Alright students, welcome back. So in this video we're going to look at sp2 type hybrid orbitals, which our example molecule is going to be trigonal planar, but of course this is going to show up in other molecules that are trigonal planar locally, right, that have that trigonal planar shape locally. So carbons that are bonded to only three things because one of their bonds is a double bond in organic all had sp2. Alright. So, our example molecule is not an organic molecule. It's boron hydride, so BH3, which Vesper theory tells us should have angles, HBH angles, of 120 degrees. Boron has an electron configuration of helium 2s2, 2p1, so we have 3 electrons to work with and the whole 2 range of orbitals. And the hydrogen has, again, 1s1, and we have 3 of them now. So we're going to need 3 orbitals to bond 3 times, right? We need 1 bond from boron to each of the hydrogens, so we're going to need 3 bonds, so we're going to need 3 orbitals. So here, let's say we use the 2s, and we need 2 of the 2p's. So I've arbitrarily chosen 2px and 2pz. Again, we could make different choices. But if we have those 3 orbitals, then we could form 3 sp2 orbitals, each having 1 electron or being available to bond 1 time. So let's draw a very large picture of our boron hydride. There's our sp2s. We're going to start drawing the other 2. That's going to get a little busy. So we'll call this one our sp2pz on boron. And now we need a sp2px on boron. This is what we've got to work with. So we could also think about where these are in relation to the bonds that we need to form to hydrogen. So we're going to label the bond going up as 1, the bond going down and to the right as 2, and the bond going down and to the left as 3. These were arbitrarily numbered. You could number them differently. So if we think about 1, this is actually aligned along the 2pz. But in order to have an sp2 hybrid orbital, we would need 1 part sp2s and 2 parts psi of one of the 2p's. Since it's aligned along 2pz, we're going to take both parts from the 2pz. So let's make our wave function, or our orbital. So we'll call this psi1 sp2. And we can think about having c1 psi2s plus square root of 2 psi2pz. Why did I use square root of 2 and not 2? Great question. If we think about taking the probability to normalize things here, remember that that square root of 2 is going to go away, and we're going to be left with c1 squared, so the square root of 2 is gone, but the square root of 2 squared in that last term becomes 2, and we're going to get c1 squared times 1 plus 2 when we do those integrals. And so c1 is going to equal, so we're going to get this 1 part to 2 parts, and c1 is going to equal the square root of 1 over 3. Alright, so we're just going to write that note up there. We already know that c1 is 1 over the square root of 3. This is a normalized wave function now. We have to account for all 3 of our orbitals, so let's also think about what bond number 2 needs. So what atomic hybridized orbital could we form to help bond in the direction that the bond 2 is going in, towards that hydrogen? So we're going to use 1 part sp2s because each one of these has to have 1 part of that s orbital. And then we need 2 parts of some p orbitals. So what p orbitals might we use if we're going in that direction of 2? It's not directly along the x-axis, nor is it directly on the z. It's in between. So the answer is we use both. We're going to use some of 2pz and some of 2px, and together they should be 2 parts to the 1 part of sp2s. In order to figure out how much 2px and how much 2pz, we'll do a little bit of trigonometry with this 30, 60, 90 triangle. So if we actually look at the x-axis, the z-axis, and then the beryllium-hydrogen bond that we want to form, we'll get a lovely 30, 60, 90 triangle. If If you don't believe me, you should prove that to yourself. All right, so we can see that along the x-axis, that's supposed to be s square root of 2. There we go, square root of 3. Along the z-axis, we have s, and along the x-axis, we have s square root of 3. So we're going to end up with psi 2s is 1 over the square root of 3, because we already proved that from psi 1. And we're going to have the same amount of psi 2s in each one. So we'll get square root of 1 over 3. Psi 2pz plus psi 2px has to give us collectively square root of 2 over 3 to make up that 2 parts. And if we look at the 30, 60, 90 triangle ratios along the x and z axis, we'll see that s should be square root of 1 over 6, which is going to mean that our z component has a constant in front of square root of 1 over 6, and our x component, our psi 2px, will have 1 over, or square root of 1 over 6 times the square root of 3, or the square root of 1/2 out front. So let's go ahead and write that wave function. So we'll get, for our second sp2 wave function, we'll get square root of 1/3 psi 2s minus the square root of 1/6 psi 2pz. The reason that we have a minus sign here is actually because of the direction that it's pointed. If we called the direction going up positive z, then the direction going down below boron must be negative z. So that is always just going to tell us direction. And then we'll get plus the square root of 1/2 psi 2px, because we'll say if that's up and right is normally what we call the positive direction, so we'll call that the positive direction. All right, so if we look at the bond we want to form for 3, that sp2 hybridized orbital from boron has to point towards that hydrogen. We're going to need 1 part psi 2s and 2 parts of 2p orbital likeness. We're going to choose the psi 2pz and psi 2px because it's very, very similar to the angle we need the sp2 to point for bond 2. It's just flipped across the x-axis. So x is going to be the opposite direction, but it's actually the exact same triangle. And so we're going to get a very, very similar wave function. So psi 3 for our sp2 is going to be square root of 1/3 psi 2s minus the square root of 1/6 psi 2pz minus the square root of 1/2 psi 2px. And again, that minus has to do with now it's in the negative x direction as opposed to the positive x direction. It's telling us which side of the orbital we're using, right? Which side is it facing? And so we'll go ahead and break the video now and take a break to digest this. And so this was the mathematical part for this sp2 hybridization. In the next video, we'll look at what do those look like visually. So we'll build up the energy diagram, and then we'll look at what the individual orbitals look like.